session will be Cody Long from Cornell University.
All right, thanks a lot, Laura. And it's really wonderful to see all of you, even if it's just virtually. So I'm going to be talking about some work mainly focusing on this first paper with Miriam, Jim, and Ling, and I'll also touch upon this paper with Mehmet, Liam, and Mike. And so to get started, let me just give you all a roadmap as to where we're going in this talk. And our claim that I'm going to establish throughout is that in an F-theory realization of the standard model, the following three statements cannot be true. One, our vacuum is a typical vacuum, meaning moderate to large H11 in the string landscape. Two, the alpha prime expansion is valid. And three, there are no additional dark 7-brane gauge sectors. So our claim is you get to choose up to two of these, but not all three simultaneously. And these conclusions are going to follow from attempting to get the standard model gauge couplings correct in F-theory. And there's a few ways that you can sort of put these statements together. But my takeaway is that this gives further evidence that we expect a large amount of dark gauge sectors in string realizations of the standard model, and also provides a pressing need for new techniques in string theory at small volumes, especially with moduli stabilization. So part one, let me just give some general expectations from exploring the F-theory landscape. So I'll be discussing F-theory, which is a strongly coupled generalization of type 2b with 7 branes. And F-theory is a really, really great place to explore, partially because we have such great mathematical tools to attack F-theory, namely algebraic geometry. So F-theory is arguably our largest playground to date in terms of number of convectifications and potential vacua we've been able to study. So mathematically, what you have is a choice of physical extra dimensions upon which you compactify type 2b. And on top of that, you assign a choice of Calabi-Yau elliptic vibration, which tracks the data of 7 branes, and in turn determines a lot of the physics, including gauge sectors, matter, and Yukawa couplings. And I should mention, flux data also plays an important role, but won't be a main player in this talk. So how does one do it? Well, after you've introduced your extra dimensional space that you compactify to beyond the physical extra dimensions, well, you introduce extra data in terms of this Calabi-Yau elliptic vibration. It's often presented in terms of this Weierstrass form, y squared is equal to x cubed plus fx plus g, where f and g are locally polynomials on the base b, but globally are sections of multiples of the anti-canonical line bundle. And the way this elliptic vibration tracks the 7-brane data is 7 branes are located at this discriminant locus, which is where the fiber, the elliptic fiber, becomes singular and pinches off. And the multiplicity of vanishing of f, g, and this discriminant locus delta determines what type of 7-brane you have and what gauge group you get as you approach different pieces of the discriminant locus. And this is determined by the classification of codimension 1 elliptic degenerations by Kodira. So given a choice of base B, well, sometimes you don't need to tune to get 7-brane stacks with gauge groups. For some bases, well, F, G, and delta have non-vanishing, multiplicity vanishing generically. So sometimes you're just stuck with gauge sectors. And these gauge groups are there for all choices of moduli, so they cannot be Higgs, at least geometrically. So these are referred to as non-Higgsable gauge groups. So there's a finite number of families of elliptically fibered Calabi-Yau fourfolds, and so we can do our best to try to explore them and see what we find. And the way we do this, the way we explore these F-theory compactifications is by starting with a base that we understand very well, and then moving through topological transitions in Calabi-Yau moduli space to explore other bases and find other physics. So what we might do is we often start with these minimal geometries. They're called weak Fano varieties, and they don't have non-Higgsable clusters. And then we can start blowing up in the base. We can start performing these topological transitions to explore the F-theory landscape. And a typical blow-up introduces non-Higgsable clusters. And these geometries, these blow-ups of these minimal weak Fano varieties, dominate the set of geometries we have available to do F-theory compactifications. So just this little graphic I have here. This is a set of blowups of point blowups of a single patch, and one can see this this weak Fano variety is this little red dot, and then as you move out, you start doing blowups. Well, every geometry, every node in this graph has non-Higgsable clusters, except for this minimal starting geometry. So these non-Higgsable clusters are very ubiquitous, and you find them very quickly when you start walking out in the F-theory landscape. So from doing ensemble studies and just exploring the different bases we have for F-theory, we find that non-Higgsable clusters are ubiquitous. For instance, in the largest known ensemble of F-theory bases, numbering greater than 10 to the 755, the probability of finding a non-Higgsable cluster is basically 1 minus 1 part in 10 to the 755. So you pretty much always find them. There are similarly strong results in random walks in toric bases done by Yan and Wadi. And the F-theory geometry, believed to be the home to the largest number of flux vacua, also has a large number of non-Higgsable clusters. And I should mention one of the geometries that Yinan will probably mention later this week, which has the largest number of axions, also has an enormous amount of non-Higgsable clusters. And these non-Higgsable clusters often have associated gauge groups. In fact, a typical gauge group, at least in this first ensemble, contains many E8 factors, many F4 factors, many E6 factors, and lots of other factors. So one expects many dark gauge sectors. So generally, just from exploring the F-theory landscape, we have some expectations from F-theory. Many dark gauge sectors, many axions, since most F-theory bases have large H11. And these are not necessarily problems, but features that you might not expect from an IR point of view and could make for some interesting model building, such as enhancements in ELP photon couplings with the number of axions, as we studied with Jim, Brent, and Gustavo. So given some evidence that we have some expectations from F-theory of large H11, so many 4 cycles, and many axions, and also many dark gauge sectors. So in this work, we're going to try to push against that second point. We're going to try to ask, can one avoid such large dark gauge sectors and engineer and find string compactifications that have only the standard model? So let's do that. Let's push back and try to evade dark gauge sectors. So if we want to avoid them, well, one seemingly necessary condition is that we have to use bases that don't have these non-Higgsable clusters. And these are the weak Fano bases I mentioned. Algebraically, they're defined by the fact that the anti-canonical bundle dots greater than or equal to 0 with any holomorphic curve C in the base. And a generic elliptic vibration of a weak Fano over a weak Fano base is smooth. Now, the challenge in just engineering the standard model is one of tadpole cancellation in this case. So if we wrap divisors Wi by 7 branes, well, with some multiplicity delta, tadpole cancellation requires that the sum over the divisors upon which the 7 branes are wrapped, weighted by their multiplicities, has to be equal to the canonical, anti-canonical, or it has to be equal to the class of the discriminant locus, which is minus 12 times the canonical class of B. And if the visible sector doesn't saturate this tadpole, well, we have leftover 7 branes. And these leftover 7 branes may provide extra gauge sectors. So let's explore this. I'm going to explore weak Fano bases, those without non-Higgsable clusters, in the context of toric geometry. So toric geometry is a very nice way to get your feet wet with geometry because much of it is combinatorial. And so a weak Fano toric threefold corresponds combinatorially to a triangulated reflexive 3-dimensional polytope. Reflexive means the only interior point is the origin, and its dual is also lattice polytope. And there are 4319 distinct reflexive polytopes, where each triangulation corresponds to a distinct geometry up to automorphisms. So because each triangulation gives a distinct geometry, the ensemble of weak Fano toric threefolds is dominated by the polytopes which emit the most triangulations, which intuitively are the polytopes with the largest number of points. So throughout this talk, I'll have the large polytopes, mainly in the back of my head. Each of these has, there are two of them, each has 38 points. So H11 of such a torque base is 35. And these geometries dominate the weak Fano torque landscape. So now I have some geometries that I want to explore. And so I'm going to attempt to engineer pure standard models or MSSMs. So to preserve supersymmetry, the 7 branes wrap effective or holomorphic force cycles known as divisors, effective divisors. And if I only want a pure standard model gauge sector, I have 2 necessary conditions that need to be fulfilled. One is that if I tune a standard model gauge group on some divisor on 7 branes somewhere, I don't induce unwanted gauge groups somewhere else as a consequence of tadpole cancellation. The second is the divisor upon which I wrap the standard model 7 branes itself must be irreducible. That is, it can't split into multiple components or else get multiple copies of the gauge group that I was trying to engineer. And these requirements reduce to polytope questions in this torque context. So since I want to talk about cycles wrapped by 7 branes, I need to talk a little bit about torque homology. So I mentioned that these torque varieties correspond to triangulated polytopes. Here's an example of a face of one such polytope. And each point on this polytope represents an effective torque divisor. And these divisors generate all divisors in the base B that corresponds to this polytope. So this is a minimal set of building blocks for all 4-cycle homology classes that are holomorphic. And the intersection structure is determined by the triangulation. Edges are curves of intersection, and triangles are points of triple intersection. So I can then represent any effective 4-cycle class in this base by labeling points on the polytope diamond with non-negative integers. And for simplicity, and because it'll come up in a bit that this is sort of a nice and natural set to restrict to, I'm going to today talk about only square-free torque divisors, where I can take linear combinations of the corresponding divisors, but my coefficients are all 1s or 0s. So we call these square-free. And the data of such a divisor is then represented by a simplicial complex, T, on the polytope. So remember, the position of the 7 branes is given by the vanishing of this discriminant locus. And if I want a standard model gauge group, well, I need to demand that this discriminant locus has a factor that corresponds to the standard model itself. But now I want to do something in addition. I want to demand that there are no additional gauge sectors. And a necessary condition for this to be true is that this residual discriminant, delta prime, cannot factorize. In terms of polytope data, well, I can write down this polynomial in the most general form quite easily in terms of local coordinates zi, complex coefficients, and the powers of local coordinates are determined by dot products of the points on the polytope with points in the dual polytope scaled out by a factor of 12. So combinatorially, I can just write down this equation. And if I want to tune a gauge group on some divisor, well, all I need is some multiplicity of vanishing. At least that's a necessary condition, which requires me to set the relevant coefficients to 0 for which the discriminant locus does not vanish along that divisor. So to tune a gauge group, I start setting some coefficients to 0 and turning off some monomials in this polynomial. So I'm going to start small. Single torque divisors correspond to points in the polytope. And I can tune a gauge group on such a divisor by placing 7 branes, or demanding a multiplicity of vanishing in the discriminant locus. So if I choose some point P on a face, say, this face is labeled by S, well, I choose to place some 7 branes on the corresponding divisor. And what happens is that if I place a point on a face, on the interior of a face, if I place 7 branes on this divisor, well, I automatically am forced with 7 branes on all divisors corresponding to the other interior points of that face. So if my tuned gauge group is on a divisor labeled by this blue dot, I'm automatically stuck with at least some 7 branes on all of these divisors. The technical proof is that there's really just one monomial protecting that face from these multiplicities of vanishing in the discriminant locus. So as soon as I try to tune a gauge group on such a divisor, well, I cut out that monomial, and then the thing that protected the other divisors corresponding to those points is gone. So now I automatically have multiplicities of vanishing along all those points interior to this face. So it doesn't matter which point I choose, any point interior to the space, if I tune a gauge group on it, well, I'm stuck with these 7 branes in red. I can try going to an edge, lowering codimension, but now, because this edge bounds this face, well, I automatically get 7 branes on all points interior to the edge and all points interior to the face. So by going down in codimension, I've made the situation worse. So any point on this edge will give the same effect. Finally, I could try to tune a gauge group on the divisor corresponding to a vertex. In that case, the vertex bounds the face and bounds 2 edges. So I automatically get 7 branes on all points interior to those edges and that face. So we started small and we found many dark gauge sectors. What happened was when we tuned a gauge group on a prime torque divisor, which is a minimal divisor in these varieties, this generically forced more 7 branes elsewhere. Technically, these need only be I1 7 branes, so they don't need to carry a gauge group. But in practice, especially in the large polytopes, there's almost always further enhancements. We find many dark gauge sectors. So let's continue. Let's push back. Let's try to avoid these dark sectors by going even bigger. So we're going to try to wrap standard model branes on linear combinations of prime torque divisors. So we're going to wrap them on a linear combination. And remember, one of the necessary conditions for no additional dark gauge sectors was that the divisor upon which we're wrapping cannot factorize, which means the corresponding line bundle has to have more than one global section. There's always the global section corresponding to the hyperplane arrangement, which is the maximally factorized thing. It's just all the coordinates multiplied together. So necessary condition is we need more than one global section. And for a square-free torque divisor corresponding to some simplicial complex, well, to count the number of corresponding global sections, there's always one, but then we add up all the vertices, all the complete edges, and all the complete faces in the simplicial complex, weighted by their generalized genus, which is defined by the number of interior points to the dual face. So we sum up all the complete vertices, edges, and faces weighted by some numbers computed by the dual polytope. And a key fact is when the polytope upon which we're working on is very large, so it's one of these polytopes that gives a large number of geometries for F-theory compactifications, these genera tend to be small. So let's consider the large polytope. All the faces, because they're facets, have genus 1, that's by definition, and all the edges have genus 0, which is a part of computation, and only a single vertex has genus greater than 0. So already it's going to be hard to get extra sections of the corresponding line bundle to prevent factorization. So let's look at this pictorially. We consider these simplicial complexes that correspond to divisors. And the key fact, just looking at one face in one of these large polytopes, is that we need to include the full face in order to not have a factorizing divisor. So I can try a bunch of divisors labeled by these points here, but unless I include the full face, even if I omit only a single point, this thing just factorizes and I get multiple copies of the gauge group I was trying to engineer. So even if I omit this point in the middle, still factorize. So finally, if I include all the points on this face, it doesn't factorize. And it's a simple combinatorial computation to see that at most a fraction of 2 times 10 to the minus 10 square-free divisors on such a large polytope do not factorize. So in order to avoid this factorization, we need to consider some large divisor. So we saw that including the full face was necessary to avoid factorization, but it's not sufficient to get a pure standard model. But going big hinted towards some structure. And it turns out if we need to go big, choosing the divisor corresponding to the anti-canonical line bundle, which is the sum over all torque divisors, is a nice choice. This divisor is a K3 surface inside the base B, and it's irreducible and smooth. And If one chooses, furthermore, a particular choice of elliptic fibration, known as the F11 fibration, this choice, choosing two seven-brane stacks on different representatives of the anti-canonical class, gives the gauge algebra SU3 cross SU2 cross U1, that of the Standard model. And an appropriate flux choice gives the exact chiral spectrum of the MSSM. Furthermore, the gauge couplings unify in the UV, even though the model is not directly a gut. And there are no dark gauge sectors arising from seven branes. Now, this is in fact independent of the polytope details as well. So we get one of these pure MSSMs for each triangulation of the polytope. And the estimate of the number of such models is order 10 to the 15. And I should emphasize that this gives the exact chiral spectrum of the MSSM. So, right, for each triangulation, we get a pure MSSM, at least the chiral spectrum, and the gauge group. And because the large polytopes admit order 10 to the 15 triangulations, well, we have found ourselves order 10 to the 15 pure MSSMs. So let's push forward. We found a large number, we sort of achieved what we wanted to do. We found a large number of pure MSSMs. We avoided the dark gauge sector problem, at least at the level of the spectrum. But now let's move beyond topology and look at the gauge couplings. Well, one requirement for these to be viable models of our universe is we need the UV gauge couplings to be large enough to be able to flow to our measured values in the IR. They can't be too tiny in the UV. One example target is the gut gauge coupling, which is 1 over alpha equals 4 pi over d squared, is about 25 at the scale of convectification, give or take a little bit. We don't have to hit this exactly. There can be some model building built in. But the point is the UV gauge couplings cannot be too tiny so they can't realistically flow to our values. And for seven brane gauge theories, well, the coupling of the corresponding gauge group is determined by the volume of the divisor that the seven brane wraps. So 4 pi over GUV squared is actually just equal to the divisor wrapped by the volume of the divisor wrapped by the seven brane, which is computed because the divisor is holomorphic by the appropriate powers of the Kähler form. So roughly speaking, we need this volume to be less than sim order 100, which is not too big. But we're going to find this will have some consequences for studying the corresponding effective field theory. So these consequences are that of control. These n equals 1 effective field theories are well behaved when the volumes of all cycles are at least some minimal number, which I'm going to take to be order 1 today. This is because there's a perturbative alpha prime curvature expansion in 1 over volume and a non-perturbative expansion in e to the minus volume for volumes of various cycles. So one could see if we make these volumes too small, we're going to have a divergent series or a badly convergent series of corrections. So for example, Kähler potential corrections delta k in these theories go as some sum dn e to the minus 2 pi n times the volume of one such curve from worldsheet instantons wrapping that curve. And these dn morally count the number of representatives of such curves in the internal space. So if we make these volumes too small, this series will not converge very well. So if we want to talk about volumes, let me introduce the Kähler cone and the Mori cone. The Kähler cone is a set of cohomology classes of Kähler forms, which are used to measure holomorphic volumes in these spaces. And the Mori cone is the dual cone, which is generated by effective curves. So the Kähler cone and the Mori cone are dual. The Kähler cone is all potential Kähler classes J, such that integral of J over any holomorphic curve is greater than 0. That should read greater than. And so let's consider the generators of the Mori cone, CA. And if we require that integrating J over CA is greater than 2 pi squared alpha prime times some number lambda, well, this implies worldsheet instant actions are greater than 2 pi times some lambda. So requiring this volume be pushed up gives us a suppression in these worldsheet instanton corrections. We'll take the string length to be equal to 1 today, and then we can define this region, this proxy region of perturbative, non-perturbative control as the stretch Kähler cone, where I demand the volumes of all holomorphic curves are at least some small number, which today will be 1. And so this is a pictorial representation of the stretched Kähler cone, this region of control. And it's at least distance 1 away from all the walls. The logic is it's hard to compute perturbative corrections as functions of general moduli. But when an effective curve is small, well, we expect to have unsuppressed worldsheet instanton corrections. So we're going to use this requirement that all curves have volume at least 1 as a proxy of control for the alpha prime expansion. Now, the key observation is that when h11 of the base is large, the condition that all curves have volume at least 1 implies some curves and some divisors are very, very large. And this is due to the fact that at large h11, the Kähler cone tends to be very narrow, which we found in work with Mehmet, Liam, and Mike. This generically, as an aside, implies an essentially massless axion, as long as the masses are generated by a superpotential. So if you thought your Kähler cone and stretch Kähler cone looks like this, more accurately large h11, they get squished so that the stretch Kähler cone and the Kähler cone are quite narrow. So a consequence is that at large h11, some of the torque divisors become very large. And since some of the torque divisors become very large, well, the anti-canonical class, which is a sum over all the torque divisors, that should be plus, is very large, which is in conflict with achieving a realistic UV gauge coupling. So the question is, how small can we make the volume of the anti-canonical class D while still remaining inside the stretched Kähler cone? So here's the problem. We're going to fix a base space, a smooth weak Fano torque threefold, and let the divisor upon which we wrap 7 branes be the anti-canonical class to achieve a pure MSSN. Our objective is to minimize the volume of such a divisor with the constraint that we keep all curve volumes greater than or equal to 1, so we're at least approximately in a region where we can control the effective field theory. And we're going to do this for each of the 4319 polytopes, 1 triangulation apiece. So here's the distribution of volumes. Our target volume was 25, which I denote with this red line here. And this is a log scale of the minimized volumes of the anti-canonical class. So this is setting our inverse gauge coupling squared up to a factor of 4 pi. Our target volume was 25, but the bulk of the distribution is greater than 10 to the 3. Now I could put some lines here, and each line indicates where all geometries at fixed h11 lie to the right of. So already at h1 equals 5, well, all geometries give volumes of minus kb at least 10. At 10, they're all at least 100. At 15, pretty much all of them are 1,000, and so on and so forth. So because each polytope can emit many triangulations, well, an overwhelming majority of the geometries is that h11 is greater than, say, 15. So most of these geometries have volumes of the anti-canonical divisor that is much too large to give a realistic UV gauge coupling. The corresponding UV gauge couplings of the geometries that lie over here at moderate to large h11 are generally just too small. Remember, this was 1 triangulation per polytope. And at h11 less than or equal to 6, well, you can just enumerate all the triangulations. There are 4,530 triangulations. But at h1 equals 35, which lived out here in this plot, there are ordered 10 to the 15. So we find that, roughly speaking, a fraction of 10 to the minus 11 of these geometries provide realistic UV gauge couplings in the stretched Kähler cone. So the bulk of the geometries lie at large h1, say 35. However, the stretched Kähler cone constraints push the gauge coupling to unrealistically small values. So if we want to wrap our standard model branes on the anti-canonical class and avoid these dark gauge sectors, one must either violate the stretched Kähler cone condition or, alternatively, be in a small h11 compactification, which is less generic. Of course, instead, one can wrap the standard model branes on a small divisor at the cost of introducing dark 7-brane gauge sectors. So let me just repeat our claim, and then I'll sum up. In a string theoretic realization of the standard model, the following 3 statements seem to not all be able to be true. Our vacuum is a typical vacuum in the string landscape with moderate to large h11. The alpha prime expansion from string theory is controlled, and there are no additional 7-brane gauge sectors. You can choose 2, but not 3 of these 3 statements. And these conclusions followed from getting the standard model gauge couplings correct in string theory. So just to end, let me just talk about some string-inspired model building from this exploration. Let's pretend for a moment, probably inaccurately, that the stretch Kähler cone satisfying theories are representative in some way of the landscape, or at least this regional landscape. Well, then we should expect a hierarchy of axion mass scales and ultralight axions, and many dark gauge sectors with hierarchies of UV gauge couplings. And one also might keep an eye out for enhanced ALP photon couplings and asymmetric axion reheating. Of course, we don't necessarily believe that these are representative. So we want to explore a region where we don't have as much control. So what happens when we get out of control? We want to know what's true in string theory. So we look where we can check. And this runs the obvious risk of a lamppost effect. And a majority of the possible standard models with the correct gauge coupling might lie at small volume outside of the stretch Kähler cone where the alpha prime expansion is not controlled. So what can be said about them? Well, I can only speculate, but if you allow me to wildly speculate for a minute, some things to look for outside the stretch Kähler cone are more intricate moduli stabilization scenarios that simultaneously involve many instanton corrections. Also heavier axions in dark sectors and strongly coupled gauge sectors at a high scale, as well as frustrated bubble nucleation cosmologies. These are hard to check with current tools, but really important problems to explore. So one might attack these with dualities, lattice results, new tools, or toy models with enhanced SUSY. Perhaps a little less speculative is that at small volume, we expect a high string scale. So if somehow we could determine that there were no or few dark gauge sectors in our universe and no nearly massless axions, this might imply our universe is one with a high string scale. And I think these are really fun and important questions to explore. And then the last thing I want to end with is to announce the summer series on string phenomenology, organized by John Stout and myself, which is a seminar series designed to highlight the work of theorists early in their careers. So every Tuesday, there's 1 hour with 2 talks, 11 a.m. to 12 p.m. Eastern. Each speaker will have 30 minutes, and the talks will be given by Zoom. And please see this website, which I can post in the Slack channel after the talk, to sign up for the mailing list or request a speaking slot. And we'll start next week. Our first speakers will be Martin Bees and Patrick Jefferson. So please tune in. And thank you.
Thank you very much, Cody, for a very nice talk. Let's see. First question from Wadi.
Oops. Click the wrong thing.
Possibly a question from Wadi. Actually, as we're waiting for Wadi to figure out his mic, can I ask you a really quick question?
Sorry.
Oh, never mind. I'll ask mine after. Go ahead, Wadi.
Sorry. Always forget to unmute. It's a very nice talk, Cody. I thought it was a very good talk. I have a quick question, which is you have this list of 3 things, and you say you can't get all 3, but you can get any 2 of them. So naively, it seems to me that it's very hard to get the first and the third. I mean, as you say, a typical Calabi-Yau at moderate to large H11 has lots of non-Higgsable stuff, which means extra 7 brane gauge sectors. So I guess the question is, do you have a reason to think that it is more natural to get a sort of a tuned standard model at smaller H11 like you were describing than, I mean, Yunnan might mention in his talk on Friday these scenarios where you have a non-Higgsable big gauge group and you flux break that to get a standard model, which would seem to me to be the easiest way to get a typical vacuum at larger H11.
Yeah, no, Wadi, I agree with that. With our usual flat measure prior, I think the non-Higgsable cluster containing geometries are much more generic. The reason it could be phrased this way is that if you just want 1 and 3, then the weak Fano varieties, of which there are a lot of, will do the trick for you. But of course, the numbers of these pale in comparison to the more generic geometries with non-Higgsable clusters.
Yeah, I guess I would imagine that would not be typical in the broader sense. And I guess I'm wondering whether you have some sense of whether the coupling or the stretched Kähler cone or something can also push you back to that regime rather than the other regime. But you were just focusing on the.
Yeah, that's a really good question. This talk was really just seeing how we could find pure standard models and then pushing against them in a new way. But it's a really interesting question to ask if there's another reason along these lines to be pushed into the non-weak Fano regime.
Okay, great.
I don't know the answer. Yeah.
Nice talk. Thanks, Cody.
Any other questions for Cody? Oh, Fabian.
Hi, Cody. Thanks for the talk.
Hey, Fabian.
I guess my question is similar to what Morty was just asking. So if I opt to get additional 7-brain dark gauge sectors, then of course I would still have the possibility of breaking these with a gauge flux. So do you have any estimate of how flux interplays with these three conditions?
I can only give you some thoughts that I've had that Jim and I have discussed a little bit recently. This is obviously a really important question to ask as to what we really expect the F3 landscape to hold. And so one might start by looking at sort of two limits in geometry, which is the geometry first that Wadi and Yinan studied with the most gauge, with the largest number of flux vacua. And in that case, most of the cycles that you would assign flux to are vertical. So even though you have a large number of choices, you might expect that generically you'd at least leave some of the gauge sectors unbroken by flux. And I want to contrast that with the geometry that Yinan will probably introduce, which has the largest number of axions, so an enormous H11, but a relatively moderate Euler characteristic compared to that, where you have a very large number of non-Higgsable clusters and many less options for flux. So I don't think there was any way you could even break all of the gauge groups in that geometry if you wanted to. I haven't done this calculation explicitly, but that's my intuition there. So these are sort of two limits you might think about, and then sort of the question is what happens in the bulk of the geometries, and that I think is something that that needs to be explored.
All right, thank you.
Thanks for the question.
Yinan?
Hi, Cody. So this statement about the gauge group tuned on the face is pretty nice in the Tarik case, but I wonder if you take a non-Tarik weak Fano threefold, and then does that phenomenon also appears, or could you avoid that?
Yeah, you can. So you can think about it locally if you add some assumptions. So if you in the toric face or the toric curve, the curve you can think about as a resolution of some A-type singularity, and the face is the normal resolution of some toric singularity. But one way to maybe generalize beyond the toric case is to think about other bases where at least some of the divisors can be thought of as resolutions of other singularities.
Okay.
And in that case, tuning gauge groups on such divisors will have a similar effect. But that's the only. I haven't thought about it beyond sort of local considerations like that. So I don't know, but it might be really interesting to explore in non-Calabi-Yau hypersurfaces that emit elliptic vibrations and other areas. Yeah, it's a great question.
Okay, thank you. So by the way, Tom actually has a question before me, so yeah, he should ask a question. Yeah, thank you.
Apologies. Sorry, yes, I missed you, Tom.
No worries. Yeah, so Cody, first of all, a clarification question. When you say here that there are no this claim that there must be these additional 7-brain dark gauge sectors if these two are satisfied, are these necessarily problematic for phenomenology?
No, they're not. This depends on crucially on things like couplings and reheating. So
Right.
They're not necessarily problematic. So the motivation here is more of what can we expect from the F3 landscape, and
Right.
what's generic before you run into problems.
Thanks. Yeah. So the other comment / question I had following up on that then is, it seems like if you have a moderate to large H11 and also you're in the stretch Kähler cone, so that you don't get very large volumes, this will necessarily mean that you have a higher dimensional Planck scale, a 10-dimensional Planck scale, which is far below the 4D Planck scale. So it seems like it could run into issues for things like grand unified theories or other physics that occurs at high energy scales due to these things. So I'm wondering to what extent you have looked into the relation between these what you're finding and some of the other high energy physics that people like to talk about?
We've looked at axion physics a bit and expectations for axion masses, but really we're just getting started in exploring this and trying to figure out the consequences. I think one goal a lot of us have in our minds of doing work like this is to try to rule out some large portion of the landscape via these considerations. So clearly the question's interesting, but no, we're still just getting started trying to understand the consequences of these large volumes.
Okay, we have two further questions. Fernando first, and then Kumran.
Yes. Hello, Cody. Well, I enjoyed your talk very much. It was very good. Thank you. Well, I have a couple of questions and comments. First, as simple questions. The 10 to the 15 MSSMs that you mentioned satisfy which of these three requirements?
Sorry. Oh, so the 10 to the 15 MSSMs. Let me get to this slide. So approximately here.
Yes. So do they satisfy which of these three requirements that you mentioned?
Some of them do. So that was what we were looking here. So they satisfy automatically that you can achieve them at moderately large H1, maximum of 35, and they satisfy by design no additional 7-brane dark gauge sectors. But what we were pushing against in here in minimizing the volumes was to trying to see if we could get the coupling right, and we found that at least in the regime of control, we generically could not for the geometries of moderate to large H11. So and more or less number 2 went wrong.
Mm-hmm. On the other hand, I mean, just for the comment, it's similar to what Tom said. Is there's nothing wrong with if about this. There's so just you found just 3 things that can be difficult to obtain simultaneously, but there's no. I mean, also, even if the goal is to eliminate models, this is a good move. I mean, eliminating all this H11, that would be a good thing.
Yeah.
Yes.
Yeah. So I think maybe one way of stating it is that, one thing you might look for in something like this is what sort of correlated physics can you find?
Mm-hmm, mm-hmm.
So, you might look for patterns and in some 1/n expansion and where n is H11 or something like this. And
Right.
some examples of some interesting physics are the enhanced photon couplings that I discussed in asymmetric reheating models, patterns in the axion couplings. But yeah, I totally agree with you that there's nothing necessarily wrong with these models.
Right. And when you were talking about the large volume, you're talking about the volume that the 7 branes are wrapping. On top of that there's the overall volume that can be even larger.
Yeah, definitely. And typically it gets pushed up to be extremely large in these large H1 compactifications in the stretch Kähler cone.
Okay, good. Okay, thank you.
Thanks, Fernando.
Kumran.
Yes, thanks. Nice talk, Cody. I had a question. So when we are thinking about the landscape of compactification, we get to F theory, we are thinking about generically, and then you have these issues about non-Higgsable clusters and large H11 and so forth. But I think without taking into account the superpotential, we might be misled by that count. In particular, I would think that these non-Higgsable clusters are always accompanied with superpotential, which drive them perhaps out of that region, in which there will be a dynamical selection process where it pushes you out to the regions smaller H11 by killing them off. Have people studied this dynamics?
No, not that I know of, but that's a really interesting idea. I'm not aware of anyone studying this.
I think that would be important if we want to assess the naturalness or whatnot in these landscapes.
Yeah, certainly. Thank you. That's a great point.
I have one really fast technical question just to finish. When you're plotting these Kähler cones and the stretch Kähler cones, are you assuming that the Kähler cone on the hypersurface descends from the toric ambient space?
So there are no hypersurfaces in this case. I'm looking at toric bases, so I know my Kähler cone exactly.
So just the base?
Yeah, for once.
Okay, thank you. All right, if there are no further questions, let's thank Cody again, and we will break until Thursday. Actually, thank all the speakers.